Welcome everyone to our video on orbital box diagrams. Before we get into this video, please make sure you've watched the two videos on electron configuration because we will be working through this video assuming that you know the rules for filling sublevels in terms of the order that they fill and are familiar with the electron configuration notation. Our learning goal for this video is simple. We're going to learn how to draw orbital box diagrams for atoms and ions. And we are going to switch right over to the whiteboard and we'll go through two examples to illustrate how this is done. For our first example, we are going to look at carbon. So this in front of us is an orbital box diagram for carbon. So carbon has an electron configuration of 1s2, 2s2, p2. Which means it has 2 electrons in an s orbital in the first energy level, 2 electrons in an s orbital in the second energy level, and 2 electrons in a p orbital at the second energy level. The first component of an orbital box diagram is the vertical axis. An orbital box diagram is representing sublevels in terms of their energies, from lowest energy to highest energy. Another term for orbital box diagrams is energy level diagrams because it's really showing the different energy levels of an atom. So we start off with the lowest energy level, 1s, drawn at the bottom, and we draw the next one above that and the next highest energy level above that, and so on and so forth. To aid in organization, we are going to group the sublevels in vertical columns. So my leftmost column will contain all of the s orbitals. My next column will contain all the p orbitals, and then d, and then f if needed. Each individual box represents an orbital, which, as you recall, is a region in space where an electron is likely to be found and has a capacity for 2 electrons. Electrons will first fill a lower energy sublevel, and once that's filled, they will start to fill the orbitals at a higher energy sublevel. For sublevels that have more than one orbital, they're drawn with connecting boxes here. So a p sublevel, 3 distinct orbitals, each which contain 2 electrons. The electrons themselves are represented by these half arrows, one pointing up and one pointing down. That is representative of the Pauli exclusion principle, or the fourth quantum number, in which electrons which occupy the same orbital have opposing magnetic moments. And we represent those opposing magnetic moments by drawing the up arrow and the down arrow. We fill from lowest to highest, but we run into something new that we did not run into with the electron configurations, in that in the electron configurations, we just list all of the electrons in a sublevel. In an orbital box diagram, we are showing how those electrons are distributed within a sublevel. So the p sublevel, 3 distinct regions, and in carbon's case, it only has 2 electrons. So we need some sort of rule for how we are going to distribute those electrons. This rule is referred to as Hund's rule. The Madelung rule gives us the rules for the order in which sublevels fill from lowest to highest energy. Hund's rule tells us how we place electrons within orbitals when all of those orbitals have the same energy. So recall that orbitals at the same sublevel are equivalent in energy. Hund's rule simply states, fill each orbital first with 1 electron and then pair them. In a p sublevel, if you have 3 or less electrons, they each occupy 1 orbital box unpaired. And only when you get to 4, 5, and 6 do you start pairing up those electrons. The reason for this is because electrons will occupy orbitals to create a structure which is the lowest possible in terms of potential energy. And when electrons occupy the same region in space, you get more electron-electron repulsion that requires the atom to use more energy to contain those electrons. And so by spreading them out into different regions in space, according to Hund's rule, the electrons are minimizing electron-electron repulsion, and thus we end up with a lower energy structure. Let's now look at another example and build an orbital box diagram or an energy level diagram from scratch. Let's look at an orbital box diagram for manganese. As practice, why don't you pause the video right now and write out the electron configuration for manganese. Here's an electron configuration for manganese. You'll note that I pulled the D sublevel out to the very end. Remember that electron configurations are not written in terms of the energy level, but they're grouped together by main energy level. And so we know that the 3D sublevel fills after the 4S. And so I'm going to just write it there for now because that's how I'm going to need to draw my energy level diagram. So my first step is to draw a vertical axis that's representing increasing energy. My next step is to start drawing the different orbitals. What I'm going to do is just draw blank orbitals, then I'll fill them afterwards. Okay, so I've got my blank structure here. Here are all the sublevels which are present in manganese. And let me just fill those with electrons. And just so it doesn't get too cluttered, I'm going to change the color. You obviously don't need to do that when you're drawing these. Okay, so I've filled all of my sublevels up until my valence level sublevel. And the D sublevel has 5 electrons. So now I'm going to apply Hund's rule. So 5 electrons, 1, 2, 3, 4, 5. So manganese has a half-filled D sublevel. The next electron would go into that first orbital box diagram there. So Hund's rule, we spread out those electrons, one in each orbital box until we have to pair them up. Now that we've gone through 2 examples, let's summarize all of the steps that we went through to draw these orbital box diagrams. And I think as I'm going through the steps, have your orbital box diagrams that you did as examples out in front of you so you can match up what I'm talking about here to what you see on the paper. First of all, we drew a vertical axis, and that axis represented increasing energy from lowest energy to highest energy. Each individual box represented one orbital. And remember, an orbital is a region in space where we are likely to find an electron. An orbital has a capacity of 2 electrons. We represent the electrons with half arrows, and we typically draw them pointing up, and then the second one that fills the orbital is pointing down. Okay, when they're paired, we have one pointing up, one pointing down, and that is representing the Pauli exclusion principle, or the 4th quantum number, where electrons within the same orbital have opposite magnetic moments. As we filled those orbital boxes, we grouped the sublevels in vertical columns. And so all of the S-type sublevels were written in the leftmost column, and then the P, D, and then F. There's no reason for that in terms of atomic structure. So that grouping does not represent anything to do with the atomic structure. It's just a visual aid to keep things organized. That's something that's important to remember when we do representations in chemistry, that there's some representations that we do to try to represent some sort of physical structure or physical meaning, but sometimes we draw things in a way because it aids simply in keeping things organized in a visual way. Next, we use our rules that we've learned, or technically the Madelin rule, for drawing sublevels from increasing energy. So 1s first, then 2s, then 2p, then 3s, then 3p, and so on and so forth. Orbitals at the same sublevel all have the same amount of energy. So we needed a rule for distributing those electrons, and that was Hund's rule. Hund's rule states that electrons will remain unpaired until they have to be paired, simply put. So we place one electron in each orbital box, and then once we have one electron in each orbital box within a sublevel, then we begin pairing them up. So that's our summary for drawing orbital box diagrams. As with everything in terms of different skills that we're learning in chemistry, the more practice you get, the more familiar you will get with the method of doing this, and the faster it will come.